All right, welcome to the last page of the notes. And what we're working with again is the scalar projector and the vector projection. So the scalar projection again is just the scalar. So it's basically giving us the magnitude of how long our projection is going to be from vector B onto A. So it's basically just giving us that scalar, it's giving us that distance. What the vector projection is, it's the actual vector. And in order to find the actual vector, what we're doing is we're just taking the scalar projection and we're multiplying it by the unit vector of A. And that's the unit vector of A. And that's how we're able to get the vector projection. That's how we're able to get the distance of our scalar projection and our distance along A. Unit vector gives us, that same direction that A is given. All right, so it says y here, and the reason why it says y is because the vector projection is the scalar projection times the unit vector. And that's how we're able to find, what that actual vector will give us. All right, so we want to find the scalar and vector projections of B onto A. So we're going to find the scalar projection first. So component of B onto A is just equal to the dot product of A and B. So -2 times 5 plus 3 times -1 plus -6 times 4 all over just the magnitude of A. So the square root of -2 squared plus 3 squared plus -6 squared. And so the numerator is going to give us -10 minus 3 minus 24. And then the denominator, so underneath the radical, we're going to get the square root of 4 plus 9 plus 36. And so the numerator looks like we're going to get -37, and in the denominator we will have the square root of 49. So -37 over 7. So that is going to be our scalar projection. And now what we want to do is we want to find our vector projection. And so what we're going to do is we're just going to take our scalar, which is -37 over 7, and we're just going to multiply it by our unit vector, which of A, which is going to be -2, 3. It looks like a -3. Let me change that. 3, -6 over 7. And so what I'm going to do is just go ahead and multiply. So -37 over -37 times -2 is going to give us 74 over 49. -37 times 3 is going to give us -111 over 49. Let me check that again. 390, 21, 111, yes. And negative 37 times negative 6 is going to give us 180, 42, 222. So 222 over 49. And that is our vector projection. Alright, now again, there's a reason why we're doing vector projection, scalar projection, because that's going to help us define, work done. And so the last part is using a formula that we have for work. So the work done by a constant force F in moving an object through a distance d as work is equal to force times distance. But this applies only when the force is directed along the line of motion of the object. So suppose, however, that the constant force is a vector F, which is PR. So instead of it being along the same line that we have, what we are is our force is being directed, somewhere above it. So because our force is directed somewhere above it, what we need to do in order to use the formula, we need to figure out, well, how can we project this vector onto the direction in which we're going? And this is what we just did. We need to find the projection vector. All right, change the color real quick. So in order to use this, keep picking the colors that are most similar to what's on here. Let's pick this poop brown. And so that's what we need. We need to be able, in order to use our formula, we need the projection vector. All right? And so that's where the projection vector comes along. So if the force moves the object from P to Q, then the displacement vector is D, which is equal to P to Q. So the work done by this force is defined to be the product of the component of the force along D and the distance moved. So in other words, instead of having to use what we found first, and converting it and showing the proof between the projection vector that we have up here to our new formula, which we have right here, all right? What we can say is, now instead of saying, F as our, instead of saying just F, that's right there, we can say it's the magnitude of F times cosine theta. So times the angle, the cosine of the angle at which we have, and that will give us that vector. All right, and times D, which again, D, lowercase d is the distance, the capital D here, because we're taking the magnitude of how far we want to go, we're just, finding the distance there. So here we have our formula. Now this formula can be rewritten to be work is defined as, or work is equal to, the displacement of vector F times the the distance or magnitude of vector F times the magnitude of vector D cosine theta, which again, we can just write the dot product, if you refer back to the beginning of the notes, is just the dot product of vector F and D. And so thus the work done by constant force F is just the dot product of F and D, where D is the displacement vector. So if we actually have the vector, both vectors, all the components of vectors F and vectors D, then we can just go ahead and skip straight to the back end of our formula right there. But if we're not given the vectors, and we're actually given the components of the vectors, but we're actually given the magnitude of vector F and vector D, then what we're able to do is just go to our formula. So let's look at an example of applying this, and I'll give you one in your notes that's very similar. Example 8 for homework. A tow truck drags a stalled car along a road. The chain makes an angle 30 degrees with the road, and the tension in the chain is 1,500 newtons. How much work is done by the truck in pulling the car 1 kilometer? And so when we're looking at doing this problem, we can go ahead and just kind of draw the vectors. All right, so we want to go a distance of 1 kilometer. There's a problem. Our question is given in newtons. Because our question is given in newtons, and newtons is a unit that uses meters instead of kilometers. What we're going to do is we're going to convert 1 kilometer to meters. So we're really working with 1,000 meters. All right. And so we want to travel a distance of 1,000 meters. And this, we could say that this is vector D. All right, that means our force vector is the chain, and it's saying it has a tension of 1,500 newtons. So we have our force vector. All right, and so all we need now is an angle, and we actually have the angle, which is 30 degrees. And so therefore, we can go ahead and plug into our formula. And I'll write that out. Work is equal to the magnitude of F times the magnitude of D cosine theta. So 1,500 times 1,000 meters times cosine of theta, which is cosine 30 degrees. 1,500 times 1,000 is 1,500,000. Cosine theta is just the square root of 3/2. And multiplying, we go ahead and half that, so 750,000 times the square root of 3. And because this is work, the unit of measure for work is joules. All right. And we're finished. So that does it for the notes. Again, if you have any questions, email me. You can come to class today if you'd like to, from 9:30 to 10:15. And that does it. And after you watch